just going to wait for the noise. There we go. Okay, so welcome everybody. It's great to see so many, or virtually see so many of you from across Leo Academies. Now, unfortunately, we're not all together in the same room to do this training. So a lot of this I'm just going to have to show you or explain, but normally I would be having lots of resources out. It'd be much more interactive. I've tried my best to make it as interactive as possible. What I always have at the start of this session for when people are virtually coming in is to have a look at the SATs question. The reason being that the majority of children that tried this question got it incorrect. And I just want us to think about why and how a bar model might help. So in a class, 18 of the children are girls, a quarter of children in the class are boys. Altogether, how many children are there in the class? Now, how would a bar model help with this question? Well, if we know that there are the class has been divided into 1/4. That means there's 4 equal parts. And if 1/4 of the children in the class are boys, that means that it's 3/4 of the class that are girls, and it is 3/4 of the class. It represents 18. Now, a bar model really clearly shows this. And I bet you're probably thinking at home what the common mistake for this question was. The vast majority of children who got this wrong tried to do 18 divided by 4 because they saw 18 and they saw 4 because they saw quarters. And this is the calculation they ended up with because they didn't represent the problem, they didn't visualize it, and this is how a bar model can help with that. So I always like to set the context for why is bar modeling useful. It's not just something we use lower down the school, it's a representation that's used all the way throughout, and this is just one example of how it can help those older children when they are calculating. I just also wanted to remind you all, I'm sure you know, but it is currently Barvember. So White Rose are currently releasing a set of bar model questions a day on their website. It's really easy to find if you just Google it. I really recommend getting stuck in with them. They've got all sorts of different levels, some with bars, some without bars. So I just wanted to sort of advertise that all to you because it's happening as we speak. So this is a great time for this session to take place. So bar modeling. I'm just going to take you through the objectives of this session. I'm really hoping we have enough time to get through it all. In this session, I would like to increase your understanding of the progression in reasoning and understanding of using bar models. I would like us to look at the different types of bar models. We're going to look at the bar models for the 4 operations. If we have time, I really hope we do, we're going to look at bar models for fractions, algebra, and problem solving. But just overall, I really want to increase your subject knowledge for using bar modeling, get you much more confident with using them in your classrooms, much more confident with recognizing questions that have bar modeling in them. So really briefly, what the research behind bar modeling says is that the ability to solve worded problems means you have to do more than just be able to calculate. And I hope that that first question has set this in context. It's not just about working with numbers, it's about knowing what to do with the numbers as well. And there can be a lot of difficulty translating information from the text into equations and into the correct equations. So in the example I showed you, it wasn't 18 divided by 4 that the children should have been doing. The ability to represent problems is really critical to success, and essentially bar modeling is a really successful way of representing problems, as I've said, right the way through. These useful representations let children reflect on representations, modify them, and make links to suitable strategies. Really briefly, it also just says that as children become more and more confident with using bar modeling in class and they get used to drawing out bar models to solve different problems, it becomes part of their cognition. So it becomes almost part of their thinking process, and that's what it is we want to happen. So what bar modeling is not. Bar modeling is not a method. We still need to teach methods, and it's not a solution to a problem. I'm going to tell you now what it is. Bar modeling is, or can be, a representation of part-whole relationships, a very helpful representation of what's happening in a problem, as I very briefly demonstrated at the start, a good way to visualize number facts and the relationship between number facts, and it is essentially a foundation for algebraic thinking. Algebraic thinking is just reasoning with unknown values. And essentially, even all the way down in early years, all bar modelling is essentially just doing a bit of algebra. And it's a scaffold to develop mathematical language from. And the NCETM talk a lot about STEM sentences, but it does form a structure for these sentences, a lot of which I'm going to show you throughout this session. And I just want to link back to the national curriculum because it's always important to do that as maths teachers. The national curriculum says that mathematics is an interconnected subject in which pupils need to be able to move fluently between representations of mathematical ideas. And here is just a really brief image to show you how bar modelling is perfect for this. You can move fluently between the representations. It connects different mathematical ideas. And also, I haven't touched on this yet, but I will. It's perfect for the CPA approach, concrete, pictorial, abstract, because you can concretely make a bar model, you can pictorially represent it, and then you have the abstract notation to go alongside, and you also have the abstract equation to go alongside the bar model as well. And just to really prove to you the versatility and the diversity of using a bar model, here is a series of bar models. They're all the same. They've all been divided into 3 equal parts. The numbers haven't changed at all. But the first set of bar models over here, or this first one here, is just looking at repeated addition, and we've got a whole that's unknown. That's typically the first way we sort of normally see bar modeling. We've then got multiplication. We've got repeated subtraction. Got a bit of BODMAS there. Now we've got division. Some more division. We've now got fractions, non-unit fractions, unit fractions and non-unit fractions, and we have ratio. That is just from one bar model. And this essentially is the bar modelling sort of curriculum over the whole of primary school. This is how you might start, and this is how it might end. Not to say that it's not okay to go between them all, but this is how versatile and useful bar modelling is throughout the whole of primary curriculum and beyond. And it's just worth noting that the bar model is actually the same, but the different mathematical concepts that are being drawn out are the thing that's changing as opposed to the bar model. You'll also see that it's different unknowns. So here we've got a whole unknown. Here we've got one part unknown. Here we've got different parts unknown. Here we don't know how many equal parts there are. But essentially it's the same bar model, just highlighting different mathematical components. And so hopefully that proves, or that demonstrates to you how versatile bar modelling is across all number strands, across all year groups. So a little bit of interactivity now in the chat, or if anyone's brave enough to unmute. I've got some different bar models, and I've labelled them all A, B, C, D, and E. If we were in a room, I'd get you to have a chat with your table or the person next to you. You're just going to have to do some thinking by yourself, I'm afraid. Which of these bar models do you like the look of, and do you think that you would use in your class with your children? Why? What bar models do you not like? And I want you to really have a think about these things. What's important about the bar model? Does it matter, for example, if the numbers are inside the bar or outside the bar? Do you need to have arrows, or should you have brackets? Does the whole need to be on top? Should the whole be on the bottom? Does it matter in what order the different parts are? What do you think it is that matters, and what does not matter? I'll give you a minute to think about that. And please, can you put your thoughts and which bar models, the letter of the bar models you like and dislike in the chat, please. So somebody's saying they would use A and C because it's similar to the part-whole model we use. I'm really glad you brought up the part-whole model, because I am going to be touching on the links between the bar modelling and part-whole models. Thank you for that. So for year 1, we've got somebody saying, I like C, as it's most like a part-whole model, and it's the simplest to read without any extra symbols. Okay, thank you, that person in year 1. So C is coming out as quite popular. And I just want to note that the bar model is actually showing exactly the same fact for all of them. it's showing 3 add 7 equals 10. So somebody else is saying A and C. So we've got A and C is coming up as popular because it's a nice visual to see 10 as the whole. And I'm so glad you've used that language. Somebody else is saying A and C. I like that C gives a good visual of how much the number is worth, if that makes sense. Yes, it does. Okay, so you're all saying what you like. What bar model or bar models would you not use and why? While I give you guys a couple of minutes to finish off what you're typing, I'm definitely going to sort of tick C and A have become firm favourites. And somebody is saying that they do not like E because it does not show the number bond clearly. Thank you for that contribution. And somebody else is agreeing, E is not clear enough for me. Okay. Thank you for all of those contributions. Please do keep them coming in. I can see the benefits of E, but it's not clear enough that 10 is the whole. Thank you. Oh, lots of people not liking E. E is not popular. I don't like E because having the numbers horizontal and vertical looks like it's showing too much information instead of the same amount. Thank you for that, guys. So it's worth noting that none of these bar models are wrong. None of them are incorrect. It doesn't matter, for example, if the whole is on top or the whole is on the bottom. Now, E is a really interesting bar model because while I agree that 7 add 3 equals 10, and that's a fact that we wouldn't disagree with, this bar model is actually not highlighting that 7 add 3 equals 10. This bar model is actually showing the difference between 7 and 3. So it's actually showing 7 take away 3 equals 4. Obviously, it's obviously not incorrect that 7 add 3 equals 10, and they are the whole together, and that's not wrong. But if we think about the structure and the layout of this bar model, 7 is actually the whole in this bar model, and 3 is a part, and we're trying to find out this missing part here. Now, lots of you like A and C, and not so much, nobody's really mentioned B and D. So as you probably have guessed, it doesn't matter if you have arrows or if you have brackets or if the number's inside or outside. But what I will say, if you were to make bar model C using physical resources, let's imagine you had seven cubes in the grey colour and 3 cubes in the green colour, and then you had 10 cubes in the blue colour. It's just really important to note that that can be misconstrued as being inaccurate because you would have 20 cubes in total and not 10 cubes in total, whereas bar models B and D don't have that potential misconception, because you'd have 7 cubes here, you'd have 3 cubes here, and the same here, you'd have your 7 and your 3 cubes, and that would be 10 overall. The potential for misunderstanding when you have the whole as a bar and you're doing it with physical resources is that you then make, or the children make, that 10 out of cubes instead of relating the fact that 7 and 3 together is 10. Not to say that it's incorrect, but it's just something to watch out for. It doesn't matter, nobody's mentioned this, but it doesn't matter if the numbers are in the bar model or outside the bar model. But what I will say is that I always put the numbers outside of the bar model, because later on when you start manipulating the bars or they're worth different amounts, it can get really messy if you've got bars that have bits crossed out of them. And it doesn't matter sort of brackets or arrows. And I would say, if I know at Leo Academy Trust we use the Maths No Problem scheme, you're most likely to come across bar model D here. Now, if you find the brackets a bit confusing, you don't need the brackets. It's not like it's an essential thing. But what the brackets do is they highlight exactly what part of the bar model is worth 7 and what part of the bar model is worth 3. And obviously all the other things I talked about don't matter. The colour of the bars, the order of them, all of that does not matter. This is what does matter when representing bar models. The size of the bar should be proportional That is, your two parts should equal your whole. Your bigger part should be bigger than your smaller parts. We cannot have a bar model where you have, if this was my 3 and this was my 7, and then we've labeled that as 10, for example, that is inaccurate. The question mark must always represent the unknown. Now, we did not have unknowns in these examples of bar models, but for example, let's imagine, if I take bar model D here, that this was the unknown. That would then link nicely to my third point, which is an equation must be written alongside the bar model. And that's really important. So this bar model D is now showing 7 add 3 equals question mark. Why is this so important? Let me cast your mind back to bar model E that we were looking at, because in this bar model, we were showcasing, actually talked about the fact that this bar model was really showing the difference between 7 and 3. So your question mark would actually be here, and your equation to match that bar model would be 7 take away 3 equals question mark. It looks like such a subtle difference, but mathematically, they are completely different operations. They're showing completely different concepts. And that's why it's really important that your question mark is representing what is the unknown variable in your bar model. Is it the part? Is it the whole? And an equation must be written alongside the bar model. Now, if you're in early years, don't think you have to be writing sort of missing number boxes next to your bar models. That's not the case. However, what you're going to be doing is laying the foundation work for the future years that will be writing equations alongside bar models. So I touched briefly on the importance of concrete pictorial abstract and why it is so important that we start representing bar models concretely. And I just had to make this quick note of do not leave them out in Key Stage 2. I've been at Brookfield this half term working with lots of Year 6, and we've been getting out the Cuisenaire almost daily to represent our different bar models. And this is an example, Year 6 example, a CPA in action. They've made concretely the bar model after Cuisenaire. They've pictorially represented it, and then they've got that abstract equation here. 1/3 is less than 2/3, and they've got the same here. And also with the algebra, 3j adds 6, and I know that the j in this question represented the number of jumps, and we've got some concrete resources out to help support. So it's just a caveat, do not leave out concrete resources in Key Stage 2. Now let's have a think about early years, or how we would introduce bar modelling if we had not. So it's not a case that you would not do all these steps in Year 4, Year 5, or Year 6, for example, but it might be that you just progress through them a bit quicker. What order would you introduce each of these if you were to try to introduce bar modelling in your class? What would come first and what would come next? Can you pop your order that you would put into the chat? So what would you start with? What would you end with? Oh, I just need to get rid of my scribblings there. Great. So lots of you are saying that you would start with C, which is completely right. This is supposed to represent the actual physical objects. So in this case, we've got 3 apples and 2 strawberries. Here, obviously, I've just got a picture of them, but it would be completely right that you would start with the concrete apples and the concrete strawberries in your classroom. So yes, you're completely right. Lots of you are coming in C, B, F, E, F, D, A. Okay, so a bit of difference. C, B, E, F, D. Okay, let's go through. So definitely, as we said, we'd start with the concrete resources, the actual physical objects that you are dealing with. And the second thing which you've all put, you would then move on to pictures of your concrete resource. At this point, it's important to note that they're still all jumbled up. What would come next would be E. It would be resources to represent your concrete objects. So in this case, my 3 apples, my 3 green apples are being represented by my 3 green cubes, and my 2 strawberries by my 2 blue cubes. We would then move on to F. This would be the next one, because now we're starting to put them into a logical structure. We're starting to group them together, and it's starting to look like what a bar model would look like. We would then, well done for you guys saying this, we would then move on to D. Now, the difference between D and F, which I've tried to show, is that F still has individual concrete resources to represent each object. D does not have individual resources to represent each object. What you have is a resource, that is a cuisinaire, that is proportional. So we do not have, I'm just going to get rid of that line of the 5. We do not have individual resources to represent the fact that the green is 3 and that the red is 2. Because if we were using cuisinaire, for example, it would be proportional. And then finally, we would move on to actually drawing out the bar model and adding in our numbers and our question mark to represent our unknown. Now, this is not to say that you would not have various steps in between. There's nothing to stop you rearranging the apples and the strawberries to form a line. There's nothing to stop you adding on the numbers to the concrete resources. There is really a sort of infinite number of steps, but I just really wanted to highlight how many there are and how crucial it is to take minute microscopic steps when introducing this concept. So this is another way that you might represent that problem. We've got 3 gems, I think they are, 3 green gems to represent our apples and 2 red gems to represent our strawberries. And this is what the children might notice. They might notice that green is 3 and 2 is red, but this is what's important, and I want you to notice the addition of this egg box container. There are 5 when it's full up. Not only have the objects in the problem, the apples and strawberries, been represented concretely, but the bar model has been represented concretely as well. The bar model is also a physical structure, and it's a physical structure that needs to be filled. Now, I've used an egg box as an example, but you might use ice cube trays, or it might literally just be as simple as drawing out something like a tens frame on a whiteboard for children to put resources in. It doesn't need to be anything fancy, but it's a structure for them to start putting in resources that they're working with. And when you use a structure for a bar model, when you're first introducing it, it highlights, for example, as this child said here, that it's 5 when it's full up, it highlights what is missing in the equation. So while in early years, you're not going to be saying 3 plus 2 equals question mark. Oh, I don't think you would be. But what you're doing with the addition of the bar model as a concrete resource is you're starting to introduce the idea. If you were to take these two red gems out, there would be a gap of 2. That's your missing number. If you were to take them all out, there'd be a gap of 5. That's a missing number. And so you're laying the foundations for that algebraic thinking and those missing number equations. Now let's have a look. We've got a slightly different problem. I've kept the numbers all very simple, so we don't have to do any calculating. David has 2 cupcakes. Maria has 3 cupcakes. How many more cupcakes does Maria have? And again, what order would you introduce each of these representations for that problem? Maria has more cupcakes than David. What would go first? What would go next, etc.? And what would you end with? And could you pop it in the chat? Yeah, as always, we've got people starting with B. So that was supposed to represent actual physical cupcakes. That would be the ideal if you had actual real cupcakes, or I suppose pictures of them. If not, to represent your cupcake problem. So that would be the first thing that you would represent. You would then, yes, absolutely, B, D, E, C, A. Yep, you would then use concrete resources to represent your cupcakes. So 1 cube representing 1 cupcake. If we then move on to E, this is supposed to represent the visual representation of the concrete resource. Something that's often missed out, I find, but it's still important that children are able to not only draw the cupcakes in this example, but also draw the concrete resource that they're representing as well. And that's really important later on when children are drawing things like deans and place counters, place value counters, that they're able to draw the concrete resource as well as the objects that they're working with. We would then move on to C, because you've got you're starting to, it's a bit more abstract now, you're starting to represent your bars just as empty blank squares. And then finally, A is the most abstract because we do not have, we have not got individual demarcation of our bars. Now, of course, and I had to quickly scribble it out because I was modelling before, You can obviously add numbers to this bit of the bar model or maybe to your concrete resources. There's absolutely nothing to stop you doing that. This is just to show you all the steps that you would take. And what's really important to note about this problem, as opposed to the previous problem that we looked at, in the previous one, we had two distinct sets of objects that we were working with the bar model. We had apples and strawberries, and they're very different, and they're very different colours. In this problem, it's just cakes. There's no distinction of objects between the two numbers. 2 and 3 are exactly the same. They're just cupcakes. They're not different flavors or sizes. They're just the same. They're just cupcakes. And so that's really important in your progression of introducing objects for using bar modeling. So the key points when you're introducing bar modeling is really use concrete materials for both objects and the bar model as well. And as I said, this can be as simple as simply drawing out a frame on a whiteboard. It doesn't have to be, if you don't have it to hand, a concrete resource, although if you have them at first, that is great. Use a bar model container with a fixed amount, so that amount does not change. So really, really powerful and really important, for example, when you're doing number bonds to 10, because you want the 10 to be the fixed amount because children are learning their number bonds to 10. Encourage children to draw objects and draw representations of objects. Make sure you're constantly exploring and defining what each number represents and link back to the object. So when they're older, link back to the word problem. 3 is the number of green apples. 2 is the number of strawberries. 5 is the number of pieces of fruit all together. And in those early years, you're not going to be using equations, but you're going to be using some sort of story alongside your bar model that's laying the foundations for the algebraic thinking later on. Any questions about that, please feel free to pop them in the chat. And I'm going to continue on to our 4 different types of bar models. Now, we were just doing a lot of work on sort of this like part, whole bar model here. This is how you can think of the 4 different types of bar modeling. You can think that there are 2 types of additive bar models, and there's 2 types of multiplicative bar models. Or you can think of it that there are 2 types of part, whole bar models, and there are 2 types of comparative bar models over here. So what is the difference between them? What I'm going to do now is I'm going to go through each of these bar models, where you use it, where they come up, and what they mean. Now, most people are most familiar and most confident with this type of bar model, the part, whole. As lots of you mentioned before, it links really nicely to our part, whole models. And that's why it's called, you know, it's showing additive relationships. It's essentially a part, whole bar model. So you have a part, add a part is equal to your whole. Really commonly used for additive relationships and fact families. Now, I want to show you this slide because it hasn't got any numbers on it, but what it is showing are all the additive relationships you can have from this bar model. And the reason I kept these as a whole bars, because I wasn't making them with concrete resources, and it was just much easier to show them as a fixed amount. So we've got whole equals part add part, whole equals part add part, part add part equals whole, part add part equals whole. Now, for the older children, this is really powerful to show them and to get them to explain what these bar models are showing them in terms of all of the additive relationships. And a bar model is really powerful for showing essentially all the different types of addition equation you can have with one number fact. And let's have a look. This is from a year 3 lesson, but don't worry so much about the numbers. I've chosen some numbers as an example, but these could equally be number bonds to 10, 2-digit numbers, 3-digit numbers, fractions, decimals, or even letters if you're doing this algebraically in year 6. So don't worry so much about what the numbers are. Think about how this can be applied to your children in your class, in your cohort. You would notice that I've got my question mark to represent my unknown. And when I've been writing out my equations, I've kept my question mark in. And that's really important, even if children know the answer, because it's important for when they don't know the answer to understand how these equations link to this bar model. We've also got some stem sentences, which I talked about. The whole is, the parts are, and. So what I'd like you to do is to have a go. Can you write all of the different equations that you can get from this part whole bar model. Can you please include, even if you've calculated, which I'm sure you're all able to do, can you keep the question mark in the equations? Pop it in the chat and have a think about, where does the question mark come up in these equations? Can you also have a go at writing out and filling in these sentence scaffolds here? And think about which bit of your sentence scaffold is the bit that you don't know. And which bit of your sentence scaffold are you going to say is unknown or are unknown? Which bit do you not know? Pop it into the chat, the equations and your sentence scaffolds. I'll give you a minute to do that. Okay, we've got some answers coming in. So our first one that we've got an example of, I'm going to start writing them in. Brilliant. 63 add 17 equals question mark. And in our next example, it's 17 add 63 equals question mark. And for the next two, question mark equals 17 add 63. Or you could have question mark equals 63 add 17. Great. Pop in your sentences if you haven't already, or I've got some already. The whole is 80, or we've worked it out. The parts are 63 and 17. Or you could have the parts are 17 and 63. Now, you were all super duper and you calculated, but what if you didn't know that what the whole was? You would have the whole is your question mark. And what I want to do, because it's going to become really important later on, is highlight where the question mark is in these equations. Look at where the question mark is. Look at where the unknown is when it's the whole. Well, what we've got here is we're highlighting the commutativity of addition. Commutativity means that it does not matter in which order you add the parts or multiply the parts, for if you're dealing with multiplication, you get the same answer. And that's a cool concept that has gone on. I think it's introduced in the early years. Commutativity of addition, it does not matter which order that you add the parts in. Your whole is always going to be the sum of those two parts. So it doesn't matter in what order the parts are, but your whole is going to be the sum of those two parts. And in these examples, we've got it either at the front of the equation or at the end of the equation here. Now let's look at the comparison model. So the part-whole comparison model, where you're looking at additive relationships. Now the big difference, even though it looks really similar to the last bar model, is this time you're comparing a larger quantity to a smaller quantity to find the difference. So I'll say that again. You're comparing a larger quantity to a smaller quantity in order to find the difference. And so your question mark would now be here. They're most commonly used with subtraction problems when you're comparing quantities, showing what is greater than or less than, that's the biggie. And then, really importantly, how many more. All of those how many more questions can be represented by this comparison model. And first of all, just as I did before, I am just going to look at the relationships. So it doesn't matter what my numbers are. I've actually taken the numbers out. I'm just focusing on the number relationships that this bar model is highlighting about subtraction. So we've got whole take away part equals part, whole take away part equals part equals whole take away part, and the other part equals whole take away part. Our sentences, they actually have not changed at all. The whole is, the parts are, and let's have a look at it with some numbers. But again, don't worry so much about the numbers. The numbers can be whatever you want them to be. They can be number 1s to 5, 2-digit, 3-digit, decimals, fractions, algebraic, doesn't matter. This is just looking at relationships. Can you have a go at writing out your equations for this bar model here? Got an example here. What would the equations be for this bar model? Can you pop them into the chat? And while you're doing that, can you have a think and tell me what's the difference about where the question mark appears now in these sets of equations? Which equations do you think children struggle with the most? I'll give you guys a minute to do that. And keep that question mark in your equations as well, as confident as I'm sure you all are in doing subtraction. And while you guys are doing that, it's worth me pointing out that the sentences have actually stayed the same. The whole is, the parts are, and okay, so we've got some answers coming in. Let me just write some of those in. Our first example, 59 take away 24 equals question mark. And that is probably what children are most familiar with for this type of problem. I think we all agree 59 take away 24 equals question mark. We then have 59 take away question mark equals 24. And then someone said what the hardest one is. Thank you. So then we've got 24 equals 59 take away question mark, or question mark take away 59, sorry, equals 59 take away 24. And someone has rightly said, or a couple of you have, that these are the most difficult for them, for the children. Let's just have a quick look at where our question mark is in these equations. It's here, it's here, it's here, and it's here. It's actually in every single spot in the equation. We cast our mind back to when we were doing this with the addition. Look, the question mark was never in that middle spot in the addition equations. How interesting. What an interesting discussion to have with your children if you've got them to do this activity. They were always attached to or next to the equal sign. And yet when you're doing it with subtraction, that question mark can just be wherever you like. And this is where it really trips children up, especially those last questions there. This is why it's so important to expose children to constructing equations like this, so that when they come across missing box equations with the different operations, they understand the properties of that equation, they understand the relationships. And you're right, these two here are the hardest. But essentially, if they understand that no matter where the equal sign is, subtraction is always a whole takeaway apart. These here, it doesn't matter if they're here and it doesn't matter if they're here, it's just going to be the other part. But children will only get that through exposure, and will only get that through this type of activity where they're constructing these equations and then looking at it without this sort of calculation or being bogged down by, for example, column subtraction. I just want to show you a mistake. This is an actual mistake that this one here that a child made. They had this bar model and they wrote 125 take away something equals 500. And then they wrote something take away 125 equals 500. And they wrote that for this bar model. Do you agree with them? What's the mistake? Now, technically, this isn't incorrect, because technically this equation could be 625 take away 125 equals 500. However, that is not what this bar model is showing us. And that's the big thing. That's just an equation that they've made from those numbers. But this bar model is showing us that 500 is the whole. And in this equation, 500 is not the whole, 625 is the whole. So that's a really important thing to point out. There's two different ways, well, there's lots of different ways you can correct this, but one way, and here's some example here with some different numbers where they've got the numbers all sort of muddled up. You could change the whole so that the parts are correct. So in this case, you could change the whole to 625 if you wanted to correct this bar model, or you could move the parts around. So you could swap the 140 and 30 so that the 110 and 30 are parts of 140. So you could either change the whole, but obviously we can't always do that in questions, can we? Or you could swap the numbers around. It's a really important mistake to highlight with the children. Essentially, what they've done is they've just confused this with addition equations. They've remembered, oh yeah, it doesn't matter which order you put the parts in, you always get the same answer, which we know is true for addition, but it's not true for subtraction. You cannot just randomly move the parts around, start subtracting any number from any number that you're given and get the same answer. That's not the case. And that's clearly the misconception that has happened here. So I just wanted to highlight, because this has actually happened to me when I've been teaching this, but really important to note that subtraction is not commutative, and the bar model helps highlight that. Ways to extend these types, working with these types of bar model with addition and subtraction. I've just got a character here, but you can put whoever you like. Mr. Mass Morris has put these three numbers into a bar model. Do you agree with him? So what's really nice about questions like this is you can either get them to change just one of the numbers, or you get them to just swap the numbers around. You could give them blank bar models and get them to come up with their own equations to write from these blank bar models. They can put their own numbers in, but essentially you're looking for the correct equations being written with the question mark in the correct place. This one I really, really like. Write 3 different bar models in your book using some of these numbers. Write the sentence scaffold next to each one. So I've chosen numbers that have relationships, so 15, 30, 45, 75, for example. So in one example, I could have 45 as my whole. That would be there. 15 is my part because it's the smaller part, and 30 is my part. And that would be a valid example. What I would want the children to do is see this 45 here as the whole, and in the next bar model, I want them to have flexibility of number, be able to manipulate these numbers, and this time 45 is going to become a part, and I'll put that with 30. So I've used them, and now 75 is my whole. And that's a really, really carefully designed activity where one number in one bar model is a part, and being able to take that number and make it whole in the next bar model. Really being able to be flexible with numbers and really having to understand the different parts that number would play in different parts of the bar model. This is nice. Giving children a bar model where it's all filled in and getting children to come up with what the question could be. And let me tell you, the child who looks at this bar model and says this word problem, 19 cupcakes and 19 cupcakes added together equals 26 cupcakes, for example, has not understood. Has not understood the calculation, but has also not understood what the bar model is showing. Equally, if a child looks at that bar model and writes the problem, I'm just going to use cupcakes again, it's making me really want cupcakes. 26 cupcakes add 19 cupcakes equals how many cupcakes? They've still not really understood it, because what this bar model is showing is the difference between 26 and 19. An appropriate word problem for this would be, I have 26 cupcakes, you have 19 cupcakes, how many more do I have? That's the kind of word problem you'd be looking for. So again, really simple, really powerful way to expose their understanding of the structure of these bar models. Moving on to the multiplicative model. So common uses with this multiplicative thinking is times bigger, times smaller, often seen with factors and multiple fact families. Later on, used with fractions and fractions of quantities, and also percentage and ratio. And also, I put that in there, you can link it to the part-whole model, but you just have many more parts. Now, let's have a look at the relationships here, because there's something really important that is different from this type of bar model to the previous bar models. I have got my multiplicative relationships here. I've got all of my relationships that have multiplication, and here I've got all of my relationships that have division. There is a huge difference between this type of bar model and the previous ones. Huge difference. First of all, the parts are now equal, and that's a big defining feature. We have not had this before, where we've had proportional parts. We've had the bigger parts bigger and the smaller parts smaller, but now the parts are equal. And another thing, I'm actually going to illustrate this point by putting a couple of numbers on. Imagine that my whole was 40 and my parts were 10. So I'll label each of them. And let's look at my first question. My part is 10, my whole is 40. Where on my bar model do I have this other number? I only have the number 40. I only have the number 10. This number is the number of equal parts. This is a derived fact. Nowhere on this bar model have I got the number 4 written. I haven't got 4 written anywhere. I've got to derive that from the number of equal parts. So that's the big important distinction between this bar model and the last types of bar model, where you had all 3 numbers up there. This time, you do not have the number of equal parts written as a number on the bar model. So that's something to point out with the children. And again, we've got all of these different types of equations, all of these different types of relationships with this derived fact, the number of equal parts. And now let's look at our sentence scaffolds, because they're different. One part, and here's my example here, I've got 20 and I've got my 5. One part is 5. There's my 5, there's my 5, there's my 5, there's my 5. There are 4 equal parts. And you'd say to the children, where's the number 4 on the bar model? Why is it not written on the bar model? Can't see it anywhere. Should it be a question mark? Is it missing? Is it left off? No, it is a derived fact from the number of equal parts. And then this sentence, that's pretty familiar. The whole is 20. Here I've got my different types of equations, which I'll go over in a second. But let's have a look at these STEM sentences now. We've got this introduction of these STEM sentences. Why are they so important? Well, let's have a look. Times bigger, times smaller. 20 is 5 times bigger than 4. 20 is also 4 times bigger than 5. But I bet you hardly ever hear it being said this way. And yet this comes up in SATs and Rising Stars and assessment questions. It always trips children up. 5 is 4 times smaller than 20. And 4 is 5 times smaller than 20. So those sentences are so needed and are so powerful. And I've seen children who know all their times table facts. They're really good with column addition, column subtraction, multiplication, division. They've got a method for each. And they come across a question that says something like, a mug is 4 times smaller than a litre jug. How much does the mug hold? They cannot answer it. They do not understand that context or that wording. A mug is 4 times smaller than a litre jug. I can't remember what I said, jug, jar. How much can the mug hold? They cannot understand that times smaller. It throws them, despite the fact that the numbers are not tricky. So it's so important that we expose children to these sentences, times bigger, times smaller. I'm going to get you guys to have a go now. Here's a bar model. I've just chosen some numbers. 280 is your whole. 70 is your parts. Can you have a go at writing out, first of all, can you write out for me all of the different equations? Now, I appreciate you don't have a division button on your keyboards, but if you just use the / button to represent division, have a go at writing all 8 equations, all 8. And I bet I know which ones you and the children would find the trickiest. I'll give you a minute to do that. And I'll start filling in our sentence scaffolds while you're writing your equations. One part is 70. There are 1, 2, 3, 4 equal parts because I've counted. And the whole is 280. So I've filled in that first one. You guys have a go at the different equations. and tell me, although you probably already can tell, which ones are you going to find the trickiest? Because it's exactly what the children will find the trickiest. I'll give you guys another minute to do that. Okay, we've got some answers coming in. Let's start writing them up. So fairly standard, the first ones, nothing too tricky, hopefully. 70 times 4 equals 280, or 4 times 70. Sorry, 4, yes, so 4 times 70 equals 280. Then we've got 280 equals 70 times 4, or 280 equals 4 times 70. Let's have a look at those addition ones. 280 divided by 4 equals 70, or 280 divided by 70 equals 4. And then I'm hoping you were thinking what I was thinking, that these ones here are most definitely the trickiest, in the same way that these ones with subtraction were the trickiest. It's subtraction and division, when the equal sign comes first, that really trip children up. You could have 70 equals 280 divided by 4, or you could have 4 equals 280 divided by 70. So well done for getting that. Can you also have a go at these 4 sentence scaffolds here? Now, most people don't have too much problem with times bigger. What are the 4 sentences that you can write for times bigger and times smaller? Pop them in the chat. I see lots of equations in the chat. Well done, guys. While you guys are writing that, I just want to make a distinction that somebody once said to me, and they were completely correct. Wouldn't for 280 divided by 70, wouldn't you need to have 70 equal parts and each of them worth 4? Now, I'm not going to draw 70 equal parts because I'll be here all night and I don't think I'd fit it all in, but you get the idea. And the answer is yes, of course, that would be an accurate bar model. That would be accurately depicting 280 divided by 70. But when you get to numbers that are, this big, you tend to do derived facts. There's nothing inaccurate with the 280 and 70 equal parts all worth 4. There's nothing wrong with that at all, but we're just going to have to look at derived facts, because otherwise it's going to be slightly impossible to draw 70 equal parts. So let's fill in some of these sentences. 280 is 4 times bigger than 70. 280 is 70 times bigger than 4. Great. So most people don't have, most children don't have too much trouble understanding that, but then we get to the times smaller, and like that example I showed you, it can throw children. 70 is 4 times smaller than 280, and 4 is 70 times smaller than 280. I bet if you'd seen this times table fact, 70 times 4 equals 280, you'd never in a million years think to link it to this sentence here. But it's so important that we do as teachers. It's so important that we expose them to all of these relationships that are going on. So when they see the question, a cup is 4 times smaller than a jug that holds 280 milliliters, they're not going to be stumped, because they're able to calculate it, but they're not stumped by the language. Okay, thanks, guys. Well done for all those sentences. They all look correct. And another common mistake is exactly like what happened before. This child has written 150 divided by 5 equals 30. Okay, so far, okay. 150 divided by 30 equals 5. Okay. 150 equals 5 divided by 30. And 150 equals 30 divided by 5. Something gone a bit wrong there. They've kept the 150 there, just like with the multiplication equations, where you always do have your whole in either side of the equal sign. They've thought, or they've mistaken the fact that multiplication is commutative, but division is not. You cannot just plonk the parts in either side of either direction and get the same answer. It does not work. So that's a common mistake that often comes up. The ways to extend this type of bar model is exactly the same. Give them blank bar models, get them to generate their own equations, having the question mark in the correct place each time. getting them to agree or disagree. And you notice here now I don't actually have the whole, it's an unknown. Do you agree that 5 is 20 times bigger than 4, for example? What's happened there? And the same thing here where I've given children a list of numbers, so 3, 6, 9, 11, 12, 18. You can see they're all linked. And the children have got to put the numbers into the bar model here. And what I'm looking for is that flexibility and that versatility with number. Can they, for example, make 6 the number of equal parts in one bar model, but in the next bar model, it is what one part is worth, for example. I'm going to finish with our last type of bar model, our multiplicative comparison model. This is where you're comparing two quantities, but the big difference now is that they have a multiplicative relationship. And you often see them with this language, times bigger, times smaller. So I've got my example here, and without actually any numbers, I'm going to explain how I would showcase this multiplicative bar model. There are 4 more red parts than blue parts. The number of blue parts is 4 times smaller than the number of red parts. And I haven't actually assigned any values at all at this point. I've just started saying the language. And I was actually doing this with year 6 at Brookfield yesterday. And oh my goodness, they really needed it. Just saying what was times bigger and what was times smaller. And here is an example of a common question that might come up where children get stuck. Mr. Johnson has 3 times as much money as Mrs. May. Mr. Johnson and, I'm sorry, when I wrote this question, I couldn't remember if Theresa May was married or not. Apologies. Mr. Johnson and Mrs. May have £120 altogether. Find the amount of money that Mr. Johnson has. Now, I will tell you what children do. They underline the key fact 3 times 120. Found the amount of money that Mr. Johnson has. They think, aha, I know what to do. I do 120 and I divide it by 3 because those are my numbers in the question. However, let's look at what the bar model is showing us. Here's Mr. Johnson. He's got 3 times as much money as Mrs. May. They have £120 altogether. It's actually 4 equal parts that you need to divide by, not 3. The 3 is corresponding to how many times greater Mr. Johnson has than Mrs. May. So this is where, and this is linked to that problem I showed you at the start, drawing it out as a bar model like this is so powerful to stop that kind of mistake. I think I had loads more to show you, but I'm aware that it's 5 now, so we're just going to end with this activity and then the evaluation. I've got a bar model here. 50 is the whole. Each of my parts are worth 10, and I've got some sentences. Can you tell me which ones you think are true or false? Is 50 5 times bigger than 10? Is 10 5 times bigger than 50? 10 is 5 times smaller than 50? 50 is 10 times bigger than 5? Can you say in the chat which ones are true, which ones are false? So I've got somebody who's saying A is true. I completely agree. 50 is 5 times bigger than 10, and C and D are true. B is not true. 10 is not 5 times bigger than 50. So brilliant, guys. Well done. I can see them all coming through now. Well done for getting that. Now, I'm so sorry that we've run out of time. My last activity for this type of bar model was going to be to come up with your own questions for this type of multiplicative bar model where you've got all these relationships. But alas, time has run out. So I'm actually going to have to forward through and just summarize what we have gone over. So in summary, teacher modeling of constructing bar models and thinking out loud is the key to success. Use concrete stories, real life stories, all the way from early years to embed understanding. And this is the important one. Bar models can really reveal the properties of the 4 operations. They really help with inverse relationships and with missing box equations. Representing your number relationships visually, so with these bar models, helps students derive other facts and relationships. And finally, Becoming familiar with bar modelling, it supports future problem solving because it increases flexibility in representing abstract information in different pictorial ways. So when they're coming across all those tricky problem solving all the way further up the school, bar modelling is going to support with that. Thank you so much for attending this training. I'm so sorry for running out of time. Can I ask you before you go, I'm just about to send it to you, so you should have it through. Could you take the last couple of minutes to fill out the evaluation form that is coming to you and really think about what was the most useful, what is going to have an impact in your classroom, what are you going to take back? And is there anything that I missed? I know I missed fractions and algebra. So, I mean, feel free to put that. I ran out of time. But what else would you require in order to support your knowledge and understanding of using bar modelling in the classroom? I read all the feedback forms, so thank you for filling them in. It really does help form the training and everything. I'm going to hang on if anybody has any questions. I'm actually going to stop recording as well. Thank you very much for attending. Please fill it in the evaluation form, and I will see you at the next maths training. Thank you.